Hello and welcome to my talk on sustainable solving, reducing the memory footprint of IFDS-based data flow analyses using intelligent garbage collection. So this title is quite a mouthful. What is it all about? First of all, I will show you what IFDS is, how it works, what is good about it, and what is bad about it. So spoiler alert, the bad parts will usually be on memory consumption. We will then look into key insights on the IFDS principles to see how we can cut down on the memory consumption without risking an algorithm that never terminates, which would be bad. And afterwards, we will look into how the edge cleanup in our sustainable solving approach really works, and then go over a few experiments. What is IFDS? IFDS is a class of problems that is interprocedural finite distributive subset problems. First of all, with all these restrictions, it may appear that these are not too many problems and it's not too applicable, but this is not correct because most of the injection problems in security, for example, such things as reflection injection, SQL injection, cross-site scripting, they are all data flow problems that can be represented as IFDS problems. The same goes for privacy leaks, for example, in Android applications. And there are popular solver implementations that solve IFDS problems, such as Heros is a pure solver, but I already mentioned the privacy leaks, also Flowdroid, which works on Android apps and Java programs. The advantages of IFDS are that it uses summaries for time efficiency. We'll see that later. It is inherently context sensitive and flow sensitive, and when Flowdroid is concerned, it's also field sensitive and object sensitive. So it's a highly precise analysis. We'll see later at what cost this comes. But before we dive into that, I'll quickly explain how IFDS works. It reduces a data flow problem to a graph reachability problem. We have data flow facts. There is the zero tautology fact, and there is one data flow fact in this simplified example per variable. So X just represents that variable X contains tainted data. In the middle, you see the interprocedural control flow graph. There is the main method on the left side, and there is a method that we just called func on the right side. So at the beginning, we have an edge from 0 to 0. That means if the tautology holds before that statement, the tautology holds after that statement, which is totally obvious. We then start propagating and insert an edge from 0 to X at the source statement. This means if the tautology holds before the source statement, then X is tainted after the source statement. This is correct because we have an unconditional taint here. We generate a new taint at the source. In the next statement, X is assigned to variable Y, and we get a new edge that says if X is tainted before the statement, then X and Y are tainted after the statement. You see, these are always edges. If X holds before the statement, then Y holds after the statement. The next line is just a call. We have a call flow function that says if X holds before that statement, then A holds inside the callee, and X holds mean X contains tainted data, and A holds A contains tainted data. And you propagate onward, and in the end, you see that we have a transitive reachability for Z at the end. So there is a path from the tautology at the start of the program to Z at the sync statement. And this means if the tautology holds at the start of the program, then Z is tainted at the end of the program. Z is passed to the sync, and hence we have found a leak. Obviously, these were just the paths that were relevant for this single leak path. And here are the remaining edges, and this is quite a large amount of edges that you get here. One important fact about IFDS is that it generates summaries. So once we have seen the method func once, we generate a summary that says incoming edges to A are propagated to the return value. And when we see a call to func again and the A parameter is tainted, we can directly conclude that the return value will be tainted and we don't need to propagate anything through func at this point. Already in this small example, you saw we got 21 edges. On real-world apps in our dataset, we had an average of 1,800 edges, going up to 13,000 edges. And this also corresponds to quite a bit of memory. So on average, we had 5 gigabytes per application for a single data flow analysis. And this went up to 17 gigabytes. But we have seen real-world examples, other data sets, where we're not talking about apps, but about backend applications that were way beyond those 17 gigabytes. So we have a memory problem here. The core idea of solving that memory problem is getting rid of edges we no longer need. So in the previous example, we showed that we accumulate more and more edges over time, and in the end, we have a path through the exploded supergraph. But we don't need that path. If we just know that we propagate to a sync statement, we can already say this is a leak. We don't need to revisit these edges anymore, and then we can delete it. And especially if we have IFDS summaries, if we know that there is a summary, and whenever this same method is called again, the summary will be plugged in instead of propagating edges through that method, then there is absolutely no need to keep the edges in memory once we have the summary. A few things to keep in mind about IFDS. So IFDS is a fixed point iteration. We have just seen straight line code here, but in general, IFDS propagates edges, and if the edge that is to be created is already in this exploded supergraph, the propagation stops, and this is the termination criterion for IFDS. So we can't just randomly remove edges, because then we remove it, add it back, remove it, add it back, and we'll never terminate. We need to keep this in mind. And secondly, modern IFDS solvers perform pointless propagation, which means we only have the frontier of edges currently in the work list being propagated. We never have an entire view of the entire exploded supergraph, because this would require synchronization of all these propagation threads, which would be way too slow. Just to keep that in mind, because we cannot reason globally here. And I already spoke about the method summaries. So let's use our straight line example and just cut it out. Assume we're at the end of the callee with our propagation, with all the threads that propagate stuff through the explode supergraph. In that case, we can safely get rid of all the edges inside the callee, because those edges have been replaced by a summary. Whenever we see a call to that method again with A being tainted, we know that the return value is tainted. We'll never ever look at those edges again, so why keep them in memory? Furthermore, we know that we can get rid of the first part of the main method, because there is, once we return from that method, no edge back to the beginning of that method. There is no loop or anything, so we'll never see that again. Get rid of it. And obviously, once we've propagated through the remainder of that method, we can get rid of those edges as well. So with our cleanup, in the end, we don't have any edges remaining in memory once we're done with everything. But that's not the key point. The key point is that already in the middle, we can remove all those edges from the explode supergraph, of which we're sure that we will never return to them. Now, this was trivial because it was straight line code. Now let's see an example that is a bit more difficult here. Let's say we have propagated over the first statement, and we then know we'll never see that statement again because there is no back edge to it. So immediately remove it from memory. Our frontier is the next statement. This is what is in the solver propagator's work list now. Once we have done that, get rid of it. Now our frontier is somewhere inside the loop. It doesn't matter where inside the loop we are. We can always return to any point inside that loop. So just assume we remove an edge here. The solver may see, okay, I've never seen that edge before, create it. We remove it, the solver returns to it, create it, and will never terminate. So we cannot just remove stuff from the loop. We have to wait until all the edges inside the loop are finished. None of our solver threads propagate anything inside that loop anymore, but at that point we can get rid of the entire loop, or all the edges inside there. This brings us to IFDS cleanup rules. So we define the frontier as those edges that are currently being propagated by at least one solver thread. And then we approximate the live edges. Obviously, everything that is in the frontier, because it's currently being propagated, is a live edge. That means we cannot delete it. And then we need the statements that are transitively reachable from the edges in the frontier. Obviously, we're talking about edges, so more precisely, we would need to compute the edges that are reachable from the frontier. But this is equivalent to the IFDS problem, right? Give me all the edges that I will visit in IFDS is equivalent to doing IFDS. So what we do here as an over-approximation is we compute the statements that are transitively reachable from the statement to which the frontier references, and then say all edges that could potentially reference one of those statements are live. And once we have the live edges, we just do the inverse, and every edge that is not live is dead and can be removed. This is a bit more complicated in Floatroid because we have interconnected solvers. There is one data flow solver and one alias solver, but just keep that aside for now. Now the evaluation, we can save about 80% of the memory consumption. The solid blue line on the left side gives you the baseline of the unmodified version of Floatroid. The solid dots give you the reduced memory consumption when we do our cleanup. On the left side, we have all the apps. On the right side, we have only those apps on which Floatroid terminates within 5 minutes without a timeout. On the x-axis, we have the frequency with which we run our garbage collection or cleanup. 0 just means always run it concurrently and do one cleanup after the other, which is approximately the best solution you can have. For timing, it's interesting that we also save time here, and this is simply because we have fewer operations on the set that contains the data flow edges, so we have fewer rehashings, and we also save time. And that's it from my side. Thank you for your attention. If you have any questions, feel free to ask. Thanks.
Hello again, everyone. We are here with our the author of our third presentation, Stephen Arts. The presentation, as you saw, has nothing to do with COVID-19, although it was in this session, and it's all about IFDS-based data flow analysis. And Stephen will be clarifying any issues and answering your questions in this session. So please start sending questions to Stephen through the chat. Stephen, perhaps while we wait for the audience to type the questions, I have a question for you. You mentioned about some optimization that you plan to do with the implementation of CleanDroid. What do you mean by this optimization? What type of optimization do you foresee that's necessary?
Well, CleanDroid itself is already an optimization of the base IFDS implementation, but it's a prototypical implementation. That means there is still some cleaning up to do. Some of the caches could actually be faster, but this is mainly engineering work and not so much algorithmic work.
Okay, thank you. And you analyze many apps, I think, if I'm not mistaken, 600 apps in your work. And in the paper, you do mention about this has not been used because it doesn't comply with this issue. This other one has not been used, but you analyze them in terms of the numbers. Did you find any correlation of the types of class? Did you come up with any classification of these types of applications with related to the findings that you have in your evaluation?
What do you mean by correlation between types of apps?
Like characteristics of some of the apps. They are quite diverse. The 600, you have completely different types of apps. But
you mean which type of app? Which type of app has we are able to save more memory on than others?
Exactly.
Well, this has to do with reachability. We're approximating the live edges by saying we take the frontier edges and then transitively compute all those units or statements that can be reached from that and consider all edges associated with those statements as potentially live. That means if you have code that has, for example, some static field that points to all sorts of other objects that again have fields and point to everything. So if everything is kind of reachable from a certain line of code, then there is little you can clean up. But if there is good separation of concern inside the app, and there is only little in the scope of a current method, for example, then you can get rid of a lot of things because you know the code won't visit it again.
Okay, thank you. Let's see if questions pop up on the chat.
Actually, this question is a bit larger because if you think about which apps take longer or require more memory in the first place, even if you don't do the CleanDroid optimization, then this is also very hard to answer. I tried to do this back then when I published FlowDroid, and there is no clear a priori distinction. You cannot say this app is like has double the lines of code, so it will take double the memory. This just isn't the case because it depends on what part of code is reachable from which part. So it's more like how densely interconnected are the statements inside your app. If you have a reference to a method, for example, and this has a lot of outgoing call graph edges because the construction of that object is very complex and you cannot really define the type, for example, and you have call graph imprecision, then this will kill off your memory. But this is nothing where you can easily say, I know that this will take a gigabyte and this will take 15 gigabytes.
Okay. So it's not based on the type of app, but it's more related to how it has been implemented.
Yes. So if you say that an app has been very well implemented and it actually does a lot of separation of concern, small modules, and so on, then you're more in luck than with an app that just puts everything together.
We have another question here from Kadire Karakaya. Kadire is asking, does the approach relate to sparse IFDS approach? And then would combining both make sense?
if you refer to jumping over statements in the code that do not propagate taint, where you say, I do not save the edge for every statement along the explode supergraph, but only for those where the taint changes. If this is the semantics of sparse IFDS, I know that there are several semantics, then yes, you could definitely combine this. This is totally orthogonal to what I did in the paper.
Okay.
I mean, I'm deleting edges from the exploded supergraph, and you're saying I insert fewer edges in the first place, which is okay, but which still allows me to remove that edges once I know that I cannot revisit them anymore.
Thank you. Any more questions? Kadira is thanking you. In the backstage, you told me that you did this as a side project from your main work. Do you plan to continue working on that?
I think the memory optimization part of Floater, that's pretty much it. I don't see too much potential to do more on that line of thought at the moment, but there is still the issue of timing, and it would be interesting to see if we can also further improve the time consumption of the static data flow analysis, even if memory is now pretty low. But there are still quite a few apps that actually time out. As I also mentioned in the paper, I have this distinction between timeout apps and non-timeout apps, and you see that quite a few have timeouts. And this would be interesting to see what can be done about that.
Good.
Yeah, as I already mentioned backstage, this is a bit of an outlier in that session, so it's different to the main topic of COVID apps. But I still hope that it was interesting to the audience.
Of course. No, the work is very nicely done, and then your presentation also was quite nice. It's really also the fact that it's early in other parts of the world, and as you can see, not so many people are present in these sessions because pretty much Europe is awake at the moment.
Okay, great. Any other questions?
No, but we should wait for the discussion room to appear, the possibility of joining the discussion room. Because if we leave the room, we may not have the possibility of joining the discussion room. And then people may come there to ask you face-to-face questions.
Mm-hmm.
Hope you enjoy the rest of the conference.
Yes. It's an interesting format to have it entirely online, but I think it's well done as part of an online conference.
Absolutely. It's very well organized. Okay, thank you again, Stephen, for joining us today and for your work. And good luck with everything.
Thank you for inviting me.
We'll be seeing you in other sessions and in your discussion room as well.